Hi, and welcome to this video on the deBroglie wavelength and the wave nature of matter. In this video, I'm going to describe what an interference pattern of light is. I'm also going to explain what it means for matter to have wave properties. And finally, I'll explain why we don't experience the wave nature of particles in our everyday life. Now, to begin, you might recall from a previous video on the wave nature of light that there were two phenomena of light that could only be described using a wave picture of light. One of those phenomena was diffraction, which is the bending of light around an obstacle or through an aperture. And the second phenomena was interference. This is where light waves can interfere with each other either constructively or destructively, depending on the amount of overlap of the wave phases. Now, both of these phenomena combine to form an interference pattern when light is shined through a two-slit apparatus. So what happens is when you shine a light source through a mask that has two small adjacent slits next to it, what happens is that the light waves then go through and diffract through the slits, forming two separate sources of new waves. And these light waves now can travel towards a photographic film and can then form a pattern on the film depending on how the individual light waves interact with each other. And what you will get is a series of bands of light and dark regions that are caused by the light waves coming from the two slits either constructively or destructively interfering. Now, in the areas on the pattern that are dark, that's due to the fact that the waves are out of phase and they're destructively interfering, whereas the light regions on that pattern are due to constructive interference, where the waves are in phase and make a bright spot. So when you actually pass a laser light through a two-slit apparatus, what you get is an interference pattern. And here's an example of an actual interference pattern that was formed with red laser light. And as you can see in the pattern, you have a central spot that's the brightest, and then you have adjacent areas of dark and light regions, which are being caused by the different types of interference between the waves. Now, this pattern can only be explained by a wave theory of light. But you might recall from another previous video that light has a wave-particle duality, meaning that sometimes you can think of light being made up of a series of waves, and other times you can think of light being made up of a series of particles or photons. So, if light, which usually acts as a wave, can behave as a particle under certain circumstances, the question might come up, what about the opposite? Can particles of matter behave as waves? Now, this might seem like a silly question, but this question was seriously considered by Louis de Broglie in 1924, and he was a French physicist. And even though he had absolutely no experimental proof that particles have wave properties, he was able to derive a mathematical relationship giving the wavelength of a particle. Now, this mathematical relationship is given as follows. It's lambda equals h over mv. Now, lambda in this circumstance is called the de Broglie wavelength, and it's given in units of meters. Now, this is the wavelength of a particle. This is not the wavelength of light. It could be the wavelength of an atom or an ion or an electron or a neutron. And h is Planck's constant, which is 6.626 times 10 to the minus 34 joules times seconds. M is the mass of the particle given in kilograms. And v is the velocity or speed of the particle in meters per second. Now, this idea that a particle can have a wave property was purely theoretical at first. And it took a couple of years for there to be actual experimental evidence that proved that particles do have wave properties. And these experiments involved the formation of interference patterns using a two-slit apparatus, except that in this time, rather than using a light source, beams of electrons were shot through the apparatus. So the setup was very similar in that you have two slits in front of a photographic film, and instead of shining light through those two slits, an electron source provided a beam of electrons that traveled through those two slits independently. And once the electrons were passed through the slits, they would be able to hit the photographic film, and we would see what kind of pattern was formed. And when this experiment was performed with a beam of electrons, the resulting pattern was that of an interference pattern, where you had central regions of bright and dark spots, just like you would get when you had light going through the double slits. So here we see an interference pattern being formed, and the only way that we can explain an interference pattern being formed is by the concept of interference between waves. So what's the consequence of this experiment? Well, the only logical explanation is that particles do indeed have wave properties, and just like light, they exhibit a wave-particle duality. So why don't we experience the wave nature of particles in the macroscopic world? Why don't we see billiard balls or baseballs or basketballs acting as waves? And to answer this, let's compare the following scenario where we have a baseball traveling at 95 miles per hour, or in SI base units it would be 42 meters per second, and let's compare that to an electron traveling at 10% the speed of light, which would be 3.0 times 10 to the 7 meters per second. Now, in order to figure out the wavelength of each of these particles, we also need to know their masses. The mass of the baseball is 145 grams, or 0.145 kilograms, and the mass of an electron is 9.109 times 10 to the minus 31 kilograms. So knowing the velocity and the mass of each of the particles, we can then calculate the deBroglie wavelength of the baseball and the deBroglie wavelength of the electron. And we calculate that the deBroglie wavelength of the baseball is 1.1 times 10 to the minus 34 meters, whereas the deBroglie wavelength of the electron is 2.42 times 10 to the minus 11 meters. Now let's compare the sizes of these two wavelengths. The deBroglie wavelength of the baseball is 10 to the minus 34. This is hugely small. This is so tiny that it's unimaginable almost. So we don't even have an apparatus that can measure something that tiny. And if you compare the size of the wavelength of the baseball to the radius of the baseball, you see that the wavelength of the baseball is over 30 orders of magnitude smaller than the size of the baseball. So even if we could detect the wavelength, it would be so small compared to the size of the baseball that it would be insignificant. However, let's take a look at the size of the wavelength of the electron. Now this is only 10 to the minus 11 meters. This is something that can actually be determined and detected. And if you compare the size of the wavelength of the electron to the radius of an electron, you see that the wavelength of the electron is 4 orders of magnitude larger than the size of the electron itself. So if we were able to shrink ourselves down to the size of an atom, we would be able to see that the wavelength of an electron compared to its size is actually quite large and significant. And so we would be able to actually experience the wave properties of an electron. Now, if we look at the consequences of the discovery of the wave properties of matter, we see that it was an important step in the formulation of quantum theory. Secondly, we're now able to think of particles in a totally new fashion and model them as waves. And so that allows us then to treat the electrons around the nucleus of an atom as being waves. And treating electrons as being waves then laid the foundation for a really important concept that we use in chemistry called atomic orbitals. And in order for us to understand atomic orbitals, we have to be comfortable with the wave nature of electrons. But atomic orbitals is going to be the topic of another video, and so we'll get to that eventually. Okay, so now that you've watched this video, you should be able to understand that particles of matter, like light, exhibit a wave-particle duality at the atomic level, and you should also be able to calculate the deBroglie wavelength of a particle and perform other associated calculations. Okay, so that's it for now. I look forward to seeing you in the next video. Take care.